Okay, this is Physics 1C for May 21st. Today we're talking about vector fields and how you can do some mathematical operations with them, divergence, curl, and then we're going to relate those ideas to things that we already know about, such as flux, and then circulation, which is kind of like a line integral. So the first thing we want to talk about is what these things are. So early on in this class, we kind of were introduced to something, I call it the del operator. There's a lot of different names for it. But it's basically this upside down triangle, and it's a vector, and it's basically it's an operator, okay, and it basically looks like this. If I take the partial derivative with respect to x times I hat plus the partial derivative with respect to y times j hat, and I add to that the partial derivative with respect to z times k hat, this is one of the representations of this mathematical object right here. And it can be used to define really three different operations, at least. There's more than this, but one of them is called the gradient, okay? So if I have some vector field, if I have a scalar field, like potential, like electric potential, and I take the Nobel operator and I multiply it by this, what you get is, well, basically something like this. You get del v del x times I hat. You basically just put the function inside of there. In this case, v is going to be some function of space, like x, y, and z, and you get this operation right here. You get this thing right here. Now, in Physics 1c, we learned that this operation here is actually related to the electric field. That if I take the gradient of a potential function of x, y, and z, then this is equal to, and the negative sign usually goes over here, it's equal to the negative of the electric field. And each one of these components here, basically, like this one here, is basically proportional to the x component of the electric field. This thing right here is called the gradient because it describes how your function varies with respect to x, y, and z. And it's kind of like a three-dimensional derivative that describes slope. Should it be dz? Oh, shoot, you're right. I missed that one. My bad. That one. Yep. Sorry about that. That should be dz. Alright. So this is a relationship that if you take the gradient of the potential, you'll get the size of the electric field. And if you want to visualize this, I can draw a pretty simple picture of how this works. So if I have a point charge, you guys know that equipotentials are basically circles that go around this object. Equipotentials are basically a line along which you have constant potential. And that if I know, for example, let's say that this is like a 10-volt line, and this is a line that represents 9 volts, and then let's say that I know the distance between these 2 points right here is like 1 centimeter, then the gradient describes exactly how quickly the voltage changes from here to here. And by describing how quickly the voltage changes, going from 10 volts down to 9 volts, if I take that and I divide by 1 centimeter, that's basically what the gradient is. It's the rate of change of this voltage with respect to, so this would be -1 volts per centimeter. It's the rate of change of the voltage with respect to distance. That's all that this is. It's just done in 3 dimensions. And this would describe basically the negative of the electric field, kind of pointing in the radial direction, you might say. So the electric field would just be equal to 1 volt per centimeter. This is actually the only lab we did in this class. You guys did a calculation like this, right? And whether you knew it or not, you were basically performing this gradient operation. Right? You guys remember doing that in the one lab we did, that you found some lines that had constant voltage, and you found the distance you measured, right? Okay. So that's effectively what the gradient is. And you could talk about gradient. Now, if you just think about what the word gradient means, like you're hiking along a trail and you see a steep slope, I guess one way to describe it is to say that slope has a really kind of steep grade to it, steep gradient. I don't know if that's a language that people would use, but yeah. So it's kind of like slope in 3 dimensions, right? So we can take this thing, it's a vector, and we've learned about different ways to do vector operations, right? So this is a vector times a scalar, and you get a vector, right? But we can do other things, right? Like we can do a dot product. Like if I want to take my novel operator here, or the del operator, and I take the dot product of that with, like, let's say, I don't know, an electric field, because this is what we're going to talk about today. And let's say this is an electric field that varies as a function of y, x, and z. Then this operation can be described by saying, okay, I basically just need to take this whole thing here. Let's copy paste this real quick. So we take this whole thing here, right? And we need to basically dot product that operator with our electric field, and the electric field is going to be written as something like this, right? It's going to be Ex times I hat plus Ey, the Y component of the electric field, times J hat plus the Z component of the electric field times K hat. Any vector can be written like this, whether it's a vector field or not. So then if I take the dot product of these two things, right, what I'm going to get is del X I hat dot product with this is going to give me basically del X of the X component of the electric field. Right? And I dot I, what's that equal to? Just remember some of your vector stuff. What's I dot I equal to? Or I hat dot I hat, sorry. Yep, it's equal to 1. So we'll just erase that. But I hat dot J hat, if you guys remember, is equal to what? What's I hat dot J hat equal to? It's 0 because they're orthogonal to each other, right? They're at right angles. So that means that when I multiply all these things out, I'm only going to get the ones that correspond to like J dot J for this one. So I'll get del E Y, del Y. And I'll do the same thing for the last one. We'll do del EZ, del Z. That was a little bit of an open mic there. That's okay, no big deal. Alright, so this is the divergence of the vector field then. Okay, so the name of this operation here, we call this operation, that's called divergence of the field. Now, what divergence represents is effectively, I mean, this is the way that I think about it. It's kind of like flux. It's like flux per unit volume, actually. So if you have a vector field that has positive divergence, I'm just going to give you an example, okay? So say you have a sprinkler, and over here, let's say we have a sink. So we have just a sink. There is a hole in the bottom along which any water in the sink is going to go, and over here we have a sprinkler, right? So the sprinkler is just going to be spraying water out in all directions. Right? It just shoots water off in all directions. Now, if I wanted to describe the velocity flow of the water as a vector field, right? And then I wanted to ask the question, suppose I take a volume of some sort, and I surround my sprinkler with it here. And I ask the question, what's the divergence of this sprinkler? Well, divergence just represents how much water is flowing kind of per second out of the volume. It's like the flow rate of the water out of the volume, okay? The sprinkler would have a divergence of this, let's say we call it the velocity of the water or something like that. This would be, oops, that's not what I wanted to write. I want to do greater than sign. This would be greater than 0 in this case. Divergence represents how much the field is flowing out of a point. Does that make sense? So a sprinkler would have positive divergence. A sink, on the other hand, where all of the water basically just swirls into the sink, right? So you've got, when you have a sink like this, you've got water that's just going to be swirling around inside of this, right? The sink, if we were to put kind of a box around it and ask what's happening to the divergence of the water flow in this case, we'd say in this case the divergence of our vector field would be negative, okay? So divergence is kind of like the flow per second per unit volume, and a sprinkler would have a positive divergence of water, and a sink would have a negative divergence of water. Water goes out, water comes in. That's what divergence is, basically. Okay. Does that make sense to you guys? Do you have any questions? Did you guys learn about this in 220? Some of you, maybe? Is there a highest possible? 3 blue, 1 brown made a video on this. Yes, he did. Yes, he did. It's really good, too. Maybe we'll watch it at the end of class, in case people haven't seen it. Or don't know about that channel. Although I'm sure a lot of you guys already know about that YouTube channel. It's really good. Is there a highest possible divergence? No. I mean, infinity, maybe. Keep in mind, divergence is a scalar, right? So... yeah, it would depend on the size of the vector, for sure. Alright, so divergence. Now, what we're describing here is vector fields now, and we'll mention some more things about that in a second, but there's one final operation that we want to discuss here, even though now you could imagine taking this operation here and starting to think about other things that you could do. In fact, there's one operation you can do is where you... Okay, let's just focus here. I don't want to get off onto... Alright, so the last one we want to talk about is curl. So, curl you get by doing this. You take that nobla vector, or the del operator, and you use the cross products with your vector field. Okay? And I think I can copy paste again, right? Yeah. Okay, so now we take the nobla thing, or the del operator, which is this right here. Yeah. And we have to cross product that with our electric field vectors. Let's take this again. And then put it right there. So we need to do that operation. Now this operation is quite a bit more complicated, right? Because now we have to start thinking about the following. Like, what is I cross I equal to? Or I hat cross I hat, what's that equal to? And I hope you remember that this is equal to 0. Any vector cross product with itself is 0. And then stuff like, what's I cross j? Okay, and I cross j is equal to positive k. You guys remember this stuff? And then if you reverse a cross product, j cross I, right, you get negative k. Right? Does this stuff look familiar to you guys? Can you reason these out for yourselves here, why those are true, by using the right-hand rule? I can go through it if you want to. Yeah, you guys are okay. I figured as much. So, that means that when I work this one out here, what I'm going to end up getting is there's going to be terms, for example, if I look at the I cross j term right here, that's the EY del EX, there's going to be a term from that one that's going to be basically del E Y del X, and then it's I cross j, so you get k hat. So that term came from basically taking this term with this term. And now we need to do it for all the other 5 combinations that we have. Hopefully you guys can see that that term crossed with that term gives you the term that I put right here. And then we go through and we do a few more. Let's look at the other one that's also going to give us a k hat. So let's look at this one, cross with this one. That one's going to give me, so it's del del y, write that one down first. And then we need to do del del y, we're doing blue and blue here. So del del y of ex. And this one is j cross I, which we said is negative k, right? So this one's going to be multiplied by negative k hat. Now, you're welcome to work out the rest of them. What you're going to end up getting is something like this. So you're going to have that's going to be the k hat term. It's going to look like that. You get that just from those first 2 terms right there. And then you're going to get an I hat term, and you're going to get a j hat term. The I hat term is going to come from the fact that if I do, I think it's j cross k, you should be able to prove that that's equal to positive I. So if I look for my j cross k term, that's going to be this term crossed with this term. That term is going to be basically del Ez del y. And then we look at the k cross j term, the opposite, which would be minus, because this will be del z of ey. So the last one has to be the combinations we haven't done yet, which is going to be our k cross I terms. And if you do k cross I, pretty sure that's equal to positive j hat. So our j hat terms, we look at the k cross I term, which is going to be del ex. So I'm doing this one and this one, del z of ex. And then minus, you can almost get the pattern here now, if you've seen what we've been doing. This next one, I don't have to even look, it has to be del ez. Oh my god, sorry for the subscripts. Del x now. And that is the definition of the curl, and it's much messier than the other one, obviously. This one represents, okay, what we call the circulation of the field per unit area. This basically represents the circulation of the fields, of the vector fields per unit area. I'm not going to write that. This is not important. So it's the circulation of the vector fields per unit area. And one way in which people describe this is to say that if you have a vector field, I'll give you an example of some vector fields real quick here. Suppose I have a vector field that's very straight and uniform, okay? Oops. In fact, we'll just use a system we've looked at before. We take a positive plate, we take a negative plate, and we put the same amount of charge on each Q over here and Q over here. This one's negative and this one's positive. And we look at the electric field in the region between the plates, and we assume that the plates are close together. We say that this electric field in this space right here is uniform, meaning that it has a constant value. You know, maybe in this case E is just equal to something like, let's say 10 volts per meter times I hat. Really, really simple electric field. Okay. Now, if I take this electric field as defined here, and I carry out all these operations, I think that just mathematically, would you agree that the curl of this vector field would be equal to 0? It's a constant, right? So basically, if I take any derivative, it doesn't matter if it's the derivative with respect to x, y, or z, every single one of these terms is 0, right? It's not turning, right? So what does it mean that it's not turning, right? So the normal way that this is described is, suppose that I place inside of this system a paddle wheel, and this paddle wheel is designed as kind of what we call a curl meter, okay? So you stick a paddle wheel right inside of here, and you ask the question, okay, is this paddle wheel going to turn if we make the assumption that the paddle wheel turns in response to the field, as if the field was some type of a force? And you say, well, not really, because if the field is the same on this side and on this side, then it's basically the paddle wheel is going to be acted on by two torques that are the same, effectively. So it's never going to spin, right? So the paddle wheel won't spin in this case, because the vector field isn't turning in any way at all. Now, we can think about, okay, paddle wheel won't turn, so the curl is 0, right? We can think about a sink, though, for example. And you can imagine if you took a little pinwheel and you stuck it in this sink, because the water's curling around like this, it's curling, that's what this is about, curl. Well, this paddle wheel probably would be able to rotate if I put it inside of this field, right? And then start thinking about some other fields that we know about, right? So let's take one of the magnetic fields we talked about in the past, okay? So suppose I have a line of current that's coming out of the page, right? So I've got current coming out like this. We know that this object will produce a magnetic field, right, around it. And that magnetic field is going to be kind of circular in nature, right? You're going to have magnetic field lines that are going to basically be these circles around here. Oops. Get more circular. More circular. Like, the magnetic field lines are basically going to look something like this. And in addition, you also know something about this. If I come out to some position arcer, we even know that the magnetic field in this case is actually just equal to mu naught times the current divided by 2 pi times the radius. Okay? You can ask the question, does this field have curl? And I would say it does, because what we could do is we could place a paddle wheel inside of here, right? And we could ask, is this paddle wheel going to turn? And I'd say, Well, the magnetic field on this side is weaker than the magnetic field on this side, so I would say that this paddle wheel is going to turn in this direction. You're going to have kind of a net torque acting on it, so that you have a circulation in this direction, right? And that's kind of what curl is. Now, if you really want to calculate what the curl of this is, well, there's two different ways you can do it. There's a definition of curl that involves radial coordinates. The other way you can do it, and you're welcome to do this yourself if you want, I'm not going to do it right now because there's a lot of other stuff I want to talk about today. You can rewrite the r vector, like I could put an xyz coordinate system here, and say that r, in this case, is equal to, well, it's two-dimensional, right? So it's going to be something like 2 pi multiplied by something like x squared plus y squared to the 1/2 power, right? And now if you're really excited about, you know, doing derivatives or whatever, you can calculate what the curl of this field is, and I think you'll find that it's not 0. It's a calculation I haven't done in a long time. Wouldn't be that hard to do. You just take the derivative with respect to x minus the derivative with respect to y, and you just go through, okay? Since no z's show up in this expression, it's not this simple, actually, because it needs to be a vector, actually, doesn't it? It's not really this simple. Yeah, I might be oversimplifying this. Don't do what I just said, because you do have to have, like, you need to know what the y component of the field is, right? And that's not super obvious from this. So you'd probably be better off, as I said, there's another version of the curl. This is in your guys' lab manual, by the way. I don't know if you know this. In your guys' lab manual, there's this whole discussion that we're basically going to be going through today. And at the end of the discussion, which starts, this is in Appendix E. Let me find out what page it's on. There's a summary of different values of the curl and the divergence and stuff. So I can find exactly where it is so I can tell you guys. Wait, isn't it the end of this? Oh, no. There it is. It's Appendix F. Is it? Okay, I'm losing my mind. One second. There we go. Appendix C, page 10. That's where it is. So if you go to Appendix C, page 10. Appendix C, by the way, contains most of the information about what we're talking about today. But it's Appendix C, page 10. You can find different values. This is in the lab manual. This is in the 1C manual, lab manual. You can see different versions of what this thing is. And this was the spherical version. Anyway, I'll let you guys read more about that if you want to. But this is like the Cartesian version. It's the one we're going to need today. All right, so I've kind of gone off on a tangent. I should stop for a second. Do you guys have any questions about curl, divergence, gradient? Specifically, divergence and curl, how they're defined, and what they represent. Any questions at all? All right, so let's apply specifically something about divergence to an actual vector field. The vector field we're going to use is this. We're going to use this picture right here for this. Is that going to pick up most of what I want? No, that's fine. So I drew this out before class because I wanted it to look reasonably good for what we're going to do today. So we have a coordinate system. All right, it's your standard kind of coordinate system. We're going to define this direction here to be the x direction. This direction here is going to be the y direction. And then positive z is going to be coming out of the board in this direction. So this is the positive z direction this way. X, Y, Z, normal coordinate system, right? Within this coordinate system, I have a box. And inside of this box, I have something. We don't really know what it is yet. But we're going to say that there's probably some kind of electric charges in this box. Okay? And the dimensions of the box that we have right here are going to be, along the x direction, this dimension is going to be dx. Along the y direction, this dimension is going to be dy. And along the z direction, which would be right here, this dimension is going to be dz. So we basically have a cube with volume that we're going to call dv. The d doesn't really mean much. It's just a volume. And the volume happens to be equal to dx times dy times dz, which happen to be the dimensions of our cube. So we basically have an infinitesimal cube. I'll say for now, and I don't think this is super important right now, but will be important later, that within our cube, we have some amount of charge, okay? And I'm just going to define the amount of charge that we have inside the cube to be dq. All right? Now there may be other charges in the system, they may be, but this represents the charge inside that volume, okay? So dq is charge in dv, okay? It's inside the cube, right? Now, I'm also going to say that there's an electric field in this region. How it's caused or what it is isn't important. It's most likely caused by charges, as electric fields often are. But I'm going to say that there is an electric field within this region, and it has values all throughout this region, okay? So there exists a vector field of an electric field. This really doesn't have to be an electric field, but we're going to use it at the end anyway, so we'll make it electric. There's an electric field that can be described in the following way. It's an electric field. It's a function of x, y, and z. And it's basically just equal to the x component of the field multiplied by I hat plus the y component of the field multiplied by j hat and plus the z component of the electric field multiplied by k hat. Now, each one of these individually, ex can be a function of x, y, and z. Ey can be a function of x, y, and z, and ez can be a function of x, y, and z. In particular, we're just going to look, I believe, at just the x direction and then kind of go from there. So what I want to say is that within this region, we've got this electric field. Let me change the color of one of these to green. And I'm going to say that on this object right here, that the vector field basically points kind of out like this, at least on the surface of that surface of the cube. Oh no. Oops. That's the value of the electric field, at least on the surface of our cube. On the right side, okay, this is going to be the electric field on the right side. I'm going to label this one to be the x component of the electric field, prime. On the left-hand side of my cube, I'm also going to have an electric field, and maybe we just copy this and move it over here. On the left side of my cube, how do I draw that? Basically, like maybe like that, maybe like that. Is it better to draw it inside? Maybe. I don't know. So on the left-hand side, we're going to have an electric field, and I'm just going to say the value of the electric field at that location, we're going to call Ex. Okay, and because it's just the X component that we're looking at here, that's why we're calling it like that. Now, there's also going to be electric field vectors on the top and bottom. Let's throw all those in. So there's going to be an electric field vector like this, and that's going to be what I'm going to call Ey prime. And then there's going to be a similar vector on the opposite side, down here. See, this is where I guess drawing it inside is kind of confusing. So maybe we do the same thing over here. Okay. So the electric field on the left side is Ex, on the top is Ey prime, on the right is Ex prime, and then on the bottom we're going to call the electric field down here Ey. So these represent, like Ex prime represents the electric field along this face. Ex is the electric field on the left face, Ey bottom face, Ey prime top face. Okay. Is this set up properly enough for you guys? There's one other thing I could say. At any point in space here, there's going to be some value for our electric field vector, right? And it might point in the x and y direction. It may have a component in the z direction, right? So that's E at a point in space, right? And you look all around the system, and maybe these are what your electric field lines look like, right? But all I'm representing, at least along this face right here, is just the component of that vector field, Ex, that points parallel to the x-axis. Okay. But a vector field in general, right, is something that it has, it's a system, right, where you have these vectors that point all in different directions, right? And what we're describing is just, this is like what a vector field would be, right? It's just like a bunch of arrows at every point in space. Instead of just having a number to represent a function, you have a vector to represent the vector field, right? Okay. Does the picture make sense to you guys? Does anyone have any questions before we start doing some mathematics? All right. So the next thing we're going to do is we're going to say, if I wanted to find the flux, or specifically the net flux, through the cube, right? We know that flux is basically defined like this. Electric flux is basically just equal to the value of the electric field multiplied by the area, right? And then you also got to multiply by the cosine of some angle between the two vectors, right? Now, in our picture here, our area vectors, I'll just draw one of them on here, they're always going to be parallel to what we chose here. So this would represent my area vector for this surface, basically, right? Maybe we call it dA. So EX prime and dA are parallel to each other, right? But on the opposite side, no, they're parallel to each other on the left side too, right? But in this case, oh, no, it's not. I'm sorry, my bad. On this side over here, what direction does the area vector point over here? Does it go to the left or does it go to the right? Or does it go up or down or something else? What direction does the area vector point on this part? Does it go inside or does it go outside? You guys remember how you do area vectors? They point out of... It goes outside. It's defined as pointing out of the surface, basically, right? So on this side, you're going to have dA pointing this way, right? So what I would say is that if I want to find the flux, right, phi e, that it's going to be equal to, at least in the x direction, something like I hate it when it does that. So remember that flux when it goes out of a surface is positive, or, you know, ex.da here is positive, and when flux comes into a surface, it's negative. So the net flux, at least in the x direction, would be something like this, right? And we can go through and do the same thing for the other directions. So there's going to be an ey prime times the surface on the bottom has dimensions dx by dz. So you multiply by dx dz. Oh my god, I'm so sorry for being confusing. This is wrong. I'm going to rewrite it because I want to do it right. So the flux through the right face is ex prime times dA. dA is dy by dz on this surface, right? So this is times dy dz. Does that make sense before I go on? That would be the flux through the right surface. And then the flux through the left surface is this, but it's negative. The value of the electric field on the left side is Ex. And we multiply this times the size of that face, the area of that face, which is dy dz. And then we do the same thing for Ey. But Ey has... it's going through a surface that's dx by dz, and then we have to subtract from this plus, same thing in the z direction, so Ez prime, it's going to be, so z is the one that comes in the front and out the back, so the face is going to be dx by dy, so this is dx dy, and then minus Ez dx dy. That's going to be my flux. It's a long, complicated expression, right? But there you go. You guys have any questions? Now, what we do next is I'm specifically going to just kind of look at this term right here and then argue that the other terms, the exact same thing happens. So what I can say is that the value of Ex prime, I'll write it down here. So this is going to be the value of the electric field at the location Ex, at the location right here on the right edge of the box. And I would argue that if I take the value of the electric fields on the left face, and I add to that the derivative of what that electric field vector is with respect to x, and then I multiply by dx, that this will give me the value of Ex prime. So take a second to look at that and see if it makes any sense to you. Now I'm going to write an equation underneath this in case this doesn't make any sense to you. Something from Physics 1A. Does that equation look familiar to you? And can you see, it's a kinematic equation. Specifically, it's the uniform velocity equation, right? It's for an object traveling with uniform velocity, so it doesn't have any acceleration, right? Can you see how these are related to each other? So x final is the position that an object is at, and to find that value, you take the initial position and you add to that its velocity times time, right? This equation above it is exactly the same. So if I want to find the electric field on the right-hand side, all I need to know is what the electric field on the left-hand side is, and I need to add to that the rate at which that field changes in the x direction, and then multiply by how far apart these points are, which is, well, it's dx in this case, right? So that expression right there just perfectly describes what the relationship is between ex prime and ex, right? And it allows us... Does that connection make sense to you guys? Are you guys okay with this? Okay, now this expression right now, what it's going to become is, I plug in for ex prime what I just wrote down there. These subscripts are just like a nightmare on this tablet. Okay, plus del E x del x. Notice that's a partial derivative now, times dx. Okay, that's ex prime. It was multiplied by dy dz. Minus... In fact, let's, here, for clarity, notice that both of these terms have a dy dz in them, right? So what we'll do is we'll just put that on the very outside. So it's ex, this is ex prime, minus ex, and then that is multiplied by dy dz. Okay? Plus dot, dot, dot. Do the same thing for these two. It's going to be 100% the same, okay? Except on the outside you'll have dx dz. Replace all the x's with y's to do the next one. And replace all the x's with z's to do the third one. You can work that one out for yourself. The nice thing that happens when we do this is that this and this cancel now, right? So now what we get is basically that the flux, okay, and I think I can write the whole thing out here, is going to be equal to, look at what we have here. It's basically going to be del ex del x. That's the only term that survives. There's a dx here times dy dz, right? So this is multiplied by dx times dy times dz. Plus, we didn't work it out, but if you do it for the y direction, you get a very similar expression. You're going to get del ey del y times, again, this one's going to be, it was dx dz, right? So you're going to get a dy out of here. You can see the pattern, right? You look at that. You're going to get you just replace all the x's with y's, you get that. And then this is times dy is dx dz, right? It's always going to be the other two. So you get the volume out of this, right? You can recognize that the volume is basically showing up in all these. And what do you have left? We have plus del ez del z, and that's also multiplied by, this one would be probably dz, and then it was dx dy. Whoops. Okay. I don't remember it today. Okay, so all in all, what we end up getting out of this is basically that the flux, okay, is equal to and then you multiply this by dx dy dz, which is just dv. Okay, that's your electric flux. That's the net flux through our system. But then you realize that this quantity right here, if we go back, which quantity is that before I scroll back up? What is that thing in parentheses equal to? No, it's not equal to E. It's divergence, yeah. So this thing, if you look at it, the partial of Ex with respect to X, the partial of Ey with respect to Y, and the partial of Ez with respect to Z, that is the definition of what divergence is. So now we can write it in even more closed form to say, let's get a new color here. So now what we've got is electric flux. Sorry. I'll write it here. So electric flux now, kind of divided by dV, is equal to the divergence of the vector field E. But we also know something about electric flux, right? Gauss's law tells us that electric flux through a closed surface is always equal to the charge inside divided by epsilon naught. Or in our problem, dq, right? That was the amount of charge we placed inside of the system, right? So plugging that in here for the flux, we end up getting basically dq over dv divided by epsilon naught. But then we recognize that, we've been doing these things in this class quite a bit where we said that, whoops. Maybe you can tell me, what would dq over dv represent? If you keep in mind what we said these things are, a cube with volume dv, dq is a charge inside dv, it's the total charge inside dv, so what would dq divided by dv represent then? It's charge density, which we usually represent with rho. If you think back to problems we've done in the past where you use something like this. So this tells us that the divergence of the vector field E is equal to the charge density rho divided by epsilon naught, or divided by the permittivity of whatever substance you're dealing with here. This would be for free space. And that is Gauss's law in differential form. The divergence of your field is directly related to the amount of charges you have inside your volume. That's what it is. And there we go. Does that make sense? If you want to do it for magnetism, you just say, okay, we'll replace the electric field with the magnetic fields, right? And once you've done that, this should be equal to 0, right? Because there's no charge density for the magnetic field, right? So these are the two forms of Gauss's law and what we call differential form. You have a positive charge, you got a positive divergence. You got a negative charge, you got a negative divergence. If you're talking about magnets, there's no such thing as that kind of charge, so any magnetic field you have is always going to have 0 divergence. And that's it. Those two expressions tell us everything we need to know about electrostatics, pretty much. In kind of a different way. It's equivalent to Gauss's law, it's just done in a different way. The Gauss's law that we learned, right, was like an integral, right? It was something like the surface integral of E dot dA was equal to, charge inside over epsilon naught. So this is like the integral form, and this is the differential form. You guys have any questions? Is all of this, digestible? Like, did you guys kind of follow what we did today? Going from this definition of what divergence, curl, and then this is right here? Is this just all, I don't know, too esoteric? Yeah, exactly. Yep. Yep. It's kind of a powerful statement if you think about it too. You always know the divergence is 0. So you can use it to solve for field, I don't know. But yeah. So our magnetic fields, right? Here. What does a magnetic field look like? So let's take this one. So let's say that I take a box. That's not a box. Box. And I enclose my magnetic field lines right here, right? Remember that flux is basically just related to the number of lines that enter. So the number of lines that go out minus the number of lines that go in, right? That's kind of what we did here. It's like the flux through this side minus this side, right? That's kind of how we did this. So in this case, you'd have flux. It's like each line that goes in also comes out. So the divergence through this box would be 0. And then I can pick whatever box I want to. It doesn't matter what it is, and the divergence will always be 0. Does that make sense? It just the nature of magnetic field lines, that they're always going to act like this. Yep. Do you guys have any other questions? So I want to do the curl part, but I also don't want to completely overwhelm you guys. And the curl one's a little more tricky. So I kind of like want to give you guys something to work on for Tuesday. I would really very much like for you guys to go and read this appendix as much as you're willing to take in. I think it's 9 pages long, and it specifically describes what we're going to do next. In particular, so it starts on page 6. You should try to read pages 6 through 9 of that appendix if you can. You can go back and read pages 1 through 5. You can do it today, you can do it tomorrow, it doesn't really matter, but I'll have you guys do that first, because I don't have a good sense, because I can't really like visualize how you're digesting this information, of if it makes any sense to you at all, and I don't want to get too fast. So I would suggest you can read all of Appendix C if you really find this stuff interesting, if you're just really interested in math. But at the very least, try to read pages 6 through 9. You don't need to understand all of it. Just kind of like sketch through it, skim through it, whatever, and like get a feeling for what's going on. And we'll talk about that next time. That sound okay to you guys? All right, stopping the recording for today. See you guys next week.